everyone. Welcome back to the webinar series. Today we're going to talk about geology. I'm with International Field Studies. My name is Haley Collins. We're going to talk about the geology of the Bahamas. I'm going to let everyone get settled and ready, and I will start right at the top of the hour at 3. If you have any questions, please write them down in the comments, and I'll get to them at the end of the webinar. Until then, just sit tight, and we will start in a few. Okay, everyone, I think I'm going to go ahead and get started. It's 3 o'clock now. If anybody jumps in later, just remember to comment your questions down below and we'll answer them at the end. So today we are going to talk about the geology of the Bahamas, and we're going to focus on 3 parts of that. We're going to focus on sedimentation, deposition, and lithification. And I will get into the explanation of these as well as what they mean to the aspects of geology in a little bit. So where did the Bahamas come from? Back about 225 million years ago, or MYA as it shows there on the screen, Pangea, or a supercontinent, was formed on Earth's surface. And this is when all of those continents, all of our continents as we know them today, were in one large formation. And then around 175 million years ago, it actually started to break apart, and we started to see the movements into the continent locations that we know today. The Bahamas actually formed from as North America and Africa plates pulled apart and South America moved down to below North America. It opened up a trench, which is what you can see right there in that white part on this map. And it opened up a really deep trench right there in the Atlantic Ocean. All of the water and sediment rushed in to fill it in. And then as the tectonic plate movements kind of slowed down, as things kind of landed where they're going, eventually landed, the sediment kept filling up and created what we called a shallow water bank. This was about 150 million years ago. So Bahamas isn't actually continental or oceanic crust. It is actually a sand bank that is built up. It made up the locations of the southern tip of Florida, Cuba, and the Bahamas. But specifically on the Bahamas, we have what's called the Grand Bahama Bank, and we'll get to see a little bit more about that later. But you can see that the formation of this area was actually a pretty cool phenomenon in the tectonics area. So let's talk a little bit about what kind of sediment we actually have here. So our main type of sediment is based off of calcium carbonate, and that is in the most common 3 forms of limestone. It's really pockmarked, it's jagged, it's got those holes, it's pretty chalky almost. We have aragonite, which has that crystalline structures. And then we also have calcite. It's still got that crystalline structure, but it's a bit more smooth. It's a bit closer to limestone. These are the 3 main types of rocks that we have here on Andros. But we also have other types of sediment that make up the sediment here in the Grand Bahama Bank, and that is eroded rock. It could come in from other locations like on the Gulf Stream, things like that. It's from pellets, which are from organisms excreting out material. It's skeletal pieces, and if you look over there to the right at that table, you can see that there is calcareous algae, foraminifera, which are tiny microscopic organisms, mollusks, and coral. All 4 of those which make up the vast majority of the skeletal grains here on the east coast of Andros, is all made up of calcium carbonate. So that just shows you that there's quite a lot of calcium carbonate in the system here on Andros and in the Bahamas. Our fourth type of sediment is called oolite or oolitic sediment. The Greek word for egg is oo, and so that's where the name of oolitic sediment comes from, because it looks quite like an egg. If you look at the photo in the top right, that is what you see of the shallow sandbanks and mudflats here. It's quite shallow water. It's a lot of rolling waves, a lot of tidal action, a lot of sunlight hitting on those flats right there. And then there's a aragonite that comes out of the water column, and it finds a piece of shell or a quartz grain or something like that, and it will attach to it. And then as the tidal action rolls those pieces back and forth over and over, it slowly starts to build up these spherical layers of aragonite in what we see in that bottom right photo there of a microscopic perfect layering of that aragonite around a main nucleus or a main shell piece or quartz grain, whatever it is. The bottom left photo is a really good close-up photo of what that oolitic sand looks like, and you can see it's really soft, it's glossy, it's smooth, unlike normal sand grains, which are spiky and jagged. So when you step on this stuff, you sink down into it. It's really nice and soft on your feet. It's actually a pretty rare form of sand that we see on Earth. It only occurs in a few places on Earth, and we actually have a large abundance of this here on the northeast end of Andros at what we call Jolter Key. It's a tire sand flat made up almost entirely of oolitic sand. So that's a really cool type of sediment that we get mixed into the sand and limestone and the formations here on Andros. Okay, so we've talked about what type of material we have. Let's talk about how it erodes, how it becomes part of that loose sand that we see on the ocean floor. Our first type of erosion, or breaking down of the material, is physical erosion. Physical erosion is most abundant in what we see as wind and waves, so it's that constant high energy crashing up against the side of large bluffs. This photo on the right is actually of Morgan's Bluff, which is on the northeast end of Andros. This is what we call our windward side of the island. There's a lot of energy, there's a lot of action, constant erosion happening, and it breaks it down by bashing up against it and pulling pieces back into the ocean. So you can see a lot of jagged formations here, a lot of sharp edges, and really high cliffs. We also have another type of physical erosion that's prevalent here called salt wedging. If you see on this photo here, there's a large depression in the side of Morgan's Bluff, looking at it from the other direction. And this actually happens from salt getting into those cracks and those crevices. And then as the water evaporates away, it leaves the salt behind, and the heat of the sun expands that salt. But because it doesn't have anywhere to go in these small crevices and cracks, it makes its own room. It pushes the rock apart, and it opens up new voids. And then more ocean waves come over the top, fill in those voids. Same process happens over and over again until eventually a large part of the rock will actually fall away from the side. And so that depression there that you can see, it's big enough to stand in easily. You could walk around into it. It's a really large chunk of the side of the bluff that fell off due to salt wedging. Our next type is called chemical erosion. This is the primary source of the breakdown of limestone here in the Bahamas. And this is due to the fact that rainwater is acidic. When you talk about acidity on the pH scale, there's acidity and basic properties, right? Rainwater is acidic, but limestone is basic. And so as this rainwater falls onto the limestone, and then as ocean waves become more acidic with climate change, it slowly dissolves away the limestone. It actually takes it and dissolves it away, and then ocean waves come over, pick up, mix it back into the ocean. That then allows those small pieces of dissolved limestone to be mixed back in and repurposed. It can become other limestone. It could become the shells of organisms. It could become the skeletons of corals, things like that. And if you look at this chemical equation below, you can see kind of that give and take, that repurposing of those materials with salt water, carbon dioxide, and calcium carbonate, or that limestone or calcite. Remember, that's the building block of all of those. Those actually can be broken down into calcium ions and bicarbonate ions, and that's the stuff, that's the material that those organisms are using for their shells and skeletons. But then at the same time, those shells and skeletons can be broken down and be reused for limestone or for calcite and things like that. So it's a constant back and forth and repurposing, and that's where that chemical erosion really has a lot of action and a lot of, it's the primary source here due to the fact that it's constant shifting and changing. Our last type of erosion that we're going to talk about is biological erosion. If you look here on the right, we have a plant that actually broke an entire rock in half. So at one point, this probably was a tiny little seed that was dropped on top of the rock. It wanted to establish its roots, so it found some pockets in the rock and it started growing, but then it needed more space and it kept growing and breaking into the rock deeper and deeper until eventually an entire tree grew in between these two pieces of rocks. We see evidence of this sometimes in what we call root casts. And if you've ever walked around on limestone, you've probably seen one and didn't realize what it was. But we actually can see depressions into the limestone and evidence of those roots snaking in between the holes and the crevices and breaking it apart until it finally was able to establish a root system for a plant. Our next type is called an organism that is called bloodtooth nearite, and it's a type of mollusk. And they actually like to feed on algae that lives inside of the rocks. So on the limestones, if you've ever seen it up close, you know that it's really pockmarked. It's got a lot of little bubbles and pockets where water and good ooey gooey algae can grow and thrive, right? And so these nearites will actually dig away at the rocks to try to get to that algae. And they actually want to break it up. And what they'll do, instead of just spitting it out to the side or moving it away, they just eat it as they're eating the algae and then filter it out later. And so they actually break up a lot of the small pieces of sediment, and then as waves come crashing over the top, it will pick up that broken down sediment and mix it back in. And it does the same repurposing as the other two types of erosion. We also have what are called fuzzy chitons, and they do a similar thing to the nearites. If you look around the edge of the photo of the chiton, it actually has a little fuzzy lip that's what it uses to suction itself in place, and it has those armored plates along the top to keep itself safe from predators and from wave action, things like that. What's really cool about chitons is that they actually will pick one place and stay there. They dig and dig and dig until they've dug themselves into a hole, sometimes a foot deep. I've had to look searching for them in the sides of limestone before, and they dig themselves really deep because they just stay in one spot and they're really focused and they just keep digging away at the limestone to get to those pockets of algae. So we've talked about the erosion and we've talked about what the sediment is made of. Let's talk about how it actually solidifies or lithifies, as we call it. It's lithification. Lith is the word for rock, and that just means the formation of that stable rock from loose sediment. So our first layer of that stabilization is what we call marine rock. This is subtidal, meaning it's below the tide zone. It stays in the water most of the time. Aragonite crystals, just like with the oolitic sediment, but this one forms a little differently, get in between those sediment pieces and lock it together. You can see in the photo to the right there, it's almost like Velcro. It locks itself into place and creates a stable rock. It recrystallizes into a rock face. As we move farther up the beach, away from the water, we get to what's called beach rock. This is on the shoreline. It's going to be equal parts in the water and out. It's where that tide is moving up and down the shoreline. This has a pretty quick process to stabilization, or to lithification as we call it. We have calcite crystals, some aragonite crystals getting into those spaces. So just like what we saw with the aragonite crystals here, there's voids in between. That's what those black spots are on the photos, right? In those voids, those calcite crystals will go in there, and because they're less dense, they can actually interlock even better, and they create an even more stable type of rock from the sunlight beating down on it and allowing those crystals to expand and fill in those voids. As we move even farther away from the water's edge, we get to what are called sand dunes. Now, this isn't going to have ocean waves bringing and depositing new calcite or new aragonite. This is going to form a little bit differently. So as the sand from the beach comes pushed over the top of the sand dune from winds and things like that, rainwater will actually take that new material on the top, the minerals, the calcium carbonate crystals, and it'll trickle it down to the bottom layer. And then we see this really dense formation, what we call dolomite, that has the least amount of space between all the sediment, and it has the most amount of crystalline structure. It fills in all those voids, and it becomes a really compact, sturdy type of rock. If you see on the photo to the right, there's people standing beside what we call an outcropping. of a sand dune lithification or of a sand dune formation there. At the very bottom where their bodies are, that lower level, you can see how dense that rock is. You can see that there's little to no void between all the sediment particles. But then as you move higher up the sand dune or up the side of this outcropping, you start to see more and more pockets. And it's not just from erosion against the side of this cutaway rock. It's actually due to the fact that as the rain washed all that material down to the bottom, it kind of left more spaces up top because it kind of trickled all of it down and condensed it down in the bottom where it lithified. So this is the types of rocks that we see here on Andros, and that's kind of how they form for each of those. But why does that matter? Why is any of that important? Why do we need to understand what erosion is or why it forms the way it does? This is a photo here of Andros, and if you look to the east side of Andros there, we have a really deep trench, and this is called the tongue of the ocean. This sits right up against the foundation or the bedrock of Andros. And it actually causes a lot of energy because it allows a lot of large waves to come crashing over the barrier reef that sits right along the east side of Andros. This is what we call the windward side of the island. It has the highest amount of energy, a lot of waves, and a lot of erosion on the east side. All of that sediment gets eroded or broken apart. It gets picked up and moved away. And that means that we are left with sharp, rocky cliffs like Morgan's Bluff that we saw in the photos before, really jagged limestone, or what we call dog-tooth limestone. It's that really spiky stuff that you would never want to walk on barefoot. So we see a lot of that kind of formation on the east side of Andros. But as we move around the north and south ends of the island, we get to what we call the leeward side. This is the side that has less energy. As the energy starts to dissipate and calm down, it drops all that sediment in one place, and that is what has formed the Great Bahama Bank. So that entire shallow mud flat and sand flat that's on the west side of the island, or on the leeward side of the island, is where all of that eroded sediment gets dropped and left behind. So in some places, this massive bank is 70 miles wide in some places. But again, why is that important to us? Why do we need to know this about islands? If we have constant erosion on the east side and constant deposition or depositing of that sand on the west side, we're going to see a kind of conveyor belt motion of the entire island system moving to the west, right? And if you have a beach house or something right on the edge of the beach on the east side of the island, eventually, and this could happen over thousands of years, it's not something that's going to happen anytime soon, but you're going to eventually see one of those stable foundations get closer and closer to the edge of the water as the beach erodes away. So that is why if you've ever been to a beach town or something like that, you see a lot of concrete structures, things like bulkheads or breakwaters, riffraff, seawalls, things like that, that people have put in place to try to stop and slow that erosion from breaking out the foundation or washing away the foundation of homes, of buildings, businesses, shipping industries, things like that. But on the flip side, on the west side, you're going to see a growth of the island. You're going to see it get larger and larger over time. So those are just things to understand about how islands slowly have a constant shift or a constant process that moves the island to the side. So now let's talk a little bit about features that we see on Andros, what we call karst features. Karst features is where we see that calcium carbonate bedrock dissolve away into horizontal and vertical and cracks and things like that, as well as caves underneath the ground. And again, this is due to that rainfall falling on the surface, and it finds those cracks and crevices, and it slowly breaks it apart and breaks it down as it falls deeper, and we eventually get karst landscape, which is what the most of Andros is made of, is karst landscape. As we walk around on the surface, there's many, many caves and cracks and fracture systems all below the surface. One of those that are really prevalent and a really obvious sign of those karst landscapes or those karst features is a blue hole. If you see in the photo on the bottom, this is actually a cave system. And at one point, this was all above water. When sea level was much lower, these caves were widening and expanding and growing. As water flowed through it from rainfall, it eventually eroded away the ceiling of the cave enough. That's what you can see in that center spike there. It eroded away the ceiling enough till it actually collapsed the ceiling in. And this is how we get sinkholes. And this is the same kind of sinkhole that you see in other places that are usually on much smaller scales. But here in this really, really abundant karst landscape, we see quite a lot of these sinkholes. And then as the sea level comes back up, it fills up with water, and that's how we have a blue hole. So it actually is dissolved away, and then it allows for it to fill up over time. Here on Andros, we have 178 freshwater or inland blue holes, and we have another 50 offshore. And they're all interconnected because those cave systems are so extensive underneath the ground that they eventually connect to the ocean and allow ocean water to get into the foundation of the bedrock. So when most people see an inland blue hole, they think the entire thing is freshwater, kind of like the cenotes that you have in Mexico. Most people believe that they're full of fresh water, but that's not actually true. It's only the first layer of the inland blue hole that is freshwater. This is what we call the freshwater lens, or what most people understand it to be is a water table. This is the actual freshwater layer that sits on top of the lower layers because it's the least dense. When we talk about density, freshwater compared to saltwater is much less dense because it doesn't have as much of the minerals and the salt and stuff that weighs saltwater down. So just like if you were to go into an inland continent or something like that and you dig down a well, you typically hit the water table after you've dug down 20, 30, even deeper sometimes. And that's when you can connect your pipe, connect your pump at the top, and you have fresh water that flows out of your well. Here on Andros, because we're on such a small amount of land, our freshwater lens is pretty deep and it's really close to the surface. So in some places it might be 10 feet away from the surface, and then as you move closer to the ocean, it's even less. It's 1-2 feet away from the surface is where you're going to see that freshwater lens. Below that freshwater lens, we have what's called the hydrogen sulfide zone. This is the point where saltwater and freshwater meet. So in that zone right there, there's a whole lot of energy and a whole lot of action going on. If you look back right here at this photo here, there's quite a lot of vegetation that sits all around the edge of the blue hole, right? There's a lot of organic matter that's going to be falling into this blue hole. As it falls in, it reaches that hydrogen sulfide zone where, remember, a lot of action, a lot of microbes live, and it actually starts to break down the organic matter. Those microbes expel energy or expel heat in an exothermic reaction, and it causes this rolling, boiling mass of energy and heat and chemical reaction happening right there in that hydrogen sulfide zone. And I've had the chance to go scuba diving in a blue hole before, and it's a really cool thing to see as you drop through that hydrogen sulfide zone. It's really murky, you can feel the warmth, and then when you hit the saltwater level, it becomes totally clear, totally cool, pristine. It's a huge layer change whenever it's a really obvious cut between the hydrogen sulfide zone and the lower below, which is the seawater zone. That seawater, again, it's connected to other caves, it's connected to other systems, and it allows fresh seawater to come in. There's not large waves, there's not large currents pushing it, but there is renewing seawater in that area. But we have organisms that live down there. It's not fish, it's not like animals like that, but there's organisms that thrive off that oxygen in that layer. But eventually, there's no more oxygen left, and we have what's called an anoxic seawater layer. This means no oxygen. There's not enough there to sustain any more life. So when you reach this level, sometimes 200, 300 feet deep, this area has no movement, no life, no mixing, no stirring of the water, and it allows for a lot of really cool things to happen. It preserves stuff down at this layer really well. If you look at the bottom of the photo, there's a pretty large hill or a mound at the bottom of the blue hole. This is all that broken down organic matter and sediment and things that are falling into the blue hole. It all layers up there perfectly and just stays for thousands of years. It doesn't get touched, it doesn't get moved, and it stratifies or layers up perfectly, and it gets preserved in those layers for thousands of years. Now, climate scientists are able to take that material down at the bottom, and they'll actually take what's called a core, or a really long section down from the deep bottom, and they can look at that material and at that organic matter and at that sediment from however long ago it was deposited there and understand what the environment looked like at that time. They can look at things from 8,000 years ago, depending on the depth of the blue hole, and understand what the environment around the blue hole was like at that time. So it's a really cool thing that we can actually look at preserved material from the bottom of blue holes. Our next type of karst feature is called a banana hole, and this is a dissolution hole, or it's a hole that was dissolved away from the surface. And if you look at the top layer right here, there is the part that we're walking on, there's not a lot of soil, right? It's pretty shallow in its actual organic matter layering up, and that's just due to the fact that it's limestone. It's a hard material, lots of wind blows it all away. It doesn't allow for a really rich topsoil or what we grow crops in. But when you look at the bottom of a banana hole, a lot of that material gets dropped down into there, but then because it's so deep, it can't come back out, and it creates this really rich soil for crops. And so farmers have used it, and people that grow banana crops especially have used these holes as ways to grow their crops, and it's been named banana holes from the fact that they grow banana crops in them. And these are similar to blue holes, but they actually are built a little bit differently. Whereas blue holes come from the bottom up and actually collapse through the ceiling, banana holes start at the surface and dissolve down, and so that's why they're called dissolution holes. This karst feature is called a speleothem. Most people know these by their other names, which are stalagmite, which means it grows from the ground because it has a G in it, and stalactite. It has a C in it, so it grows from the ceiling. These grow in gaseous oxygen. They have to have air around them for them to form. So again, it has we have one of those cave systems below the ground. Rainwater comes trickling down into the cracks and crevices of this cave, and it starts dripping all of that stuff that it picked up on the way. It drops minerals and calcium carbonate and a whole bunch of stuff, and it drops it into the actual cave, and it forms in these icicle-like formations from the ceiling and then straight below it from the ground, and they actually form up and down to each other till they eventually meet, like some of the photos here. We also have caves that are now underwater though. So if you look at this photo here, this is someone scuba diving on the bottom left in a cave system. And remember how I was saying earlier, in these cave systems, when we get to the point where they're deep enough, it actually preserves things underwater really well. And so these people here are actually exploring an underwater cave. At one point though, that cave had to be above ground, because remember I said that those speleothems that we're seeing right there, or those stalagmites and stalactites, had to be formed in air. So at one point the sea level was low enough for this cave to form speleothems. And then they were able to go down there and they collected one. If you see on the right here, this is actually a photo of a stalagmite, meaning from the ground, that someone has cut in half and looked at. And if you look at the acronyms there, the first one at the very top says 15K or 15,000, and then BP stands for beyond present. So that layer right there, the part that was on the outermost layer, was formed 15,000 years ago. As we move lower, it's 60,000 years ago, and then 66, and even 153,000 years ago is when that material formed on this icicle stalagmite. So it's crazy to think, but we can use these speleothems just like with that sediment from the bottom of the blue holes, because they're perfectly preserved for thousands of years. Climate scientists and geologists have used speleothems to understand what climates and what the environment looked like 153,000 years ago by looking at the minerals and the materials that are inside of these speleothems. Now we have, this is a map system, or a map of a blue hole system here called Guardian Blue Hole. This is down in the south part of North Andros. Brian Cook and Brad Pacell mapped out this entire cave system as far as they possibly were able to, and as you can see, they went for a distance of 2,207 feet and up to a depth of 450 feet in some places. But if you look really closely, there's question marks all over this map. They got to a point where they just weren't able to go any farther. They weren't able to map farther, whether they ran out of air or it was just too dangerous to go into, because these can be pretty dangerous cave systems. And they are actually able to map out this extensive cave system just in this one small area. Now, if you think about the entirety of Andros, it's covered in these underwater labyrinths, just like this one. And they're all interconnecting, and they're all covering the bottom of the bedrock here. So as we walk around, like I was saying earlier, as we walk around, we're probably walking above extensive cave systems. And again, when the water was much lower, organisms like crocodiles, alligators, tortoises, which only live on land, were living and using these cave systems for shelter, and for humans use them to store things or to live in during storms, things like that. But then after the remains were left and the water came back up, again, it preserved them in these pristine conditions. So not only geologists and climate scientists can use these blue holes to their advantage and these cave systems to their advantage, paleontologists and archaeologists can also use them. They can actually go down and find these perfectly preserved remains of animals and humans, understand the culture as well as the animals that lived here in whatever time these animals died. And so we can actually use these underwater labyrinths for a lot of things and to our advantage. If you have any questions, I'm going to take them right now. I'm going to go look at the questions here, but I really hope you enjoyed learning a little bit about blue holes and geology of the Bahamas. I'm trying to pull up the comment section right now. 1 second. Please put any questions you have now on there, and I will pull them up and answer them as they come, okay? Okay, so my first reply first, Brian Cook, thank you very much for commenting and watching my presentation. Really hope you enjoyed it. He said, nice map, less question marks on the map these days, so he's definitely gone and continued on with his exploration of that cave system. We have Carrie Jareen, who said they're giving a talk on karst geology of the Bahamas tomorrow evening for a caving club in Texas. So if anybody's interested, go and check out their karst geology. Maybe you can ask her in the comments and learn more about the geology of Texas. Shayna Factor said, how does the entire island not collapse into the cave systems? It was posted by Eli, their 12-year-old. Actually, it's really cool, but because it's such an interwebbing system and the limestone is still relatively strong, it is able to still hold up a lot of weight and things like that. Eventually, we will see it erode away whenever maybe the next low sea level comes and erodes away more. But at the last low mean sea level, which is whenever the sea level was much lower, it only eroded to this point and then it stabilized. So it is okay to walk down and it's not going to collapse or anything like that. But it is still pretty extensive and really cool to think that there's such an interlocking system underneath our feet. I see another question from Kim Collins. It says, what is the deepest a beginner diver might go in a blue hole? It depends on your level of training, but typically beginner divers can go to about 60 feet. So you would reach, probably in some blue holes, you might be able to reach the hydrogen sulfide zone, but most hydrogen sulfide zones here start around 70 to 80 feet, so you might not get to see anything but freshwater as a beginner diver. But if you keep going on in your dives and learn a bit more, advanced divers can go down to 130 feet, so you'll definitely get to see some of those layering then. And I have been able to go to 100 feet in one of the blue holes that we have here. It's called Cousteau's Blue Hole. And I was able to go through, again, like I said, that hydrogen sulfide zone and reach the saltwater layer. And I was able to see that perfect shimmering layer above my eye, like my eyesight, where the hydrogen sulfide zone stopped. So it was a really cool experience to get to pass through that zone. I have another question from Jeremiah Walters. It says, when stalagmites and stalactites meet, what is the term they're called? You wrote columns. Yeah, columns is one of them. We also have things called pillars. Some of them, as they get larger and more extensive, can be called curtains. There's a lot of different geological terms for it, but it's pretty cool to see. I typically call them columns or pillars. Alice Ellender wrote, have you dived in any of the caves? I have dived not into a full cave system. I'm not trained to do that. That is a different specialization called cave diving, sometimes called cavern diving, depending on how deep you're going, things like that. I have not gone into a cave system as of yet. I do hope to one day, but after I've had the adequate training for it and learned a lot more about the cave systems here. Shanna Factor wrote, how do the different layers like hydrogen sulfide not mix with the other layers? That is due to the density of those layers. So freshwater is the least dense. If you've ever done those like chemical experience where you mix like oil and water and the oil and water separate into different layers, this is kind of a similar thing in that the salt water sits down below because it's much more dense than the freshwater. And then the anoxic salt water sits even lower because it's much colder and there's no oxygen, so it actually allows it to become even less dense, and it layers up like that just due to their different densities. Carrie Dreen said, this sounds familiar, but is there any specific reading you suggest on the topic? I don't have any off the top of my head about specific like reading that you can find on Karst topography and things like that. I've done a lot of research over the years. I actually did some research in my undergrad on blue holes in the Bahamas that if you want any more information, I can definitely give you a list of things after this, but off the top of my head right now, I can't really give you any. I would suggest just looking up blue holes in the Bahamas and things like that, and you'll probably find a pretty extensive list of scientific research that people have done, because it is a very common place to come and do research on blue holes because they are so prevalent here. Just looking for more questions really quick. Okay, guys, well, if that's everything, I hope I got to answer everybody's questions. I just want to say thank you again for listening in with us and tuning in. Next week, we have a webinar on mangroves with Alex. And we also, please look out for our mini-sodes that we post every week. We post them on our website at intlfieldstudies.org, on Facebook and on YouTube. So please go check those out and learn a little bit more about what we're doing here. Thank you again for tuning in, and have a good day.